Dear students, let us continue the third unit of chemistry, the classification of elements and periodicity in properties. In this session, we will start with the periodic table, how it is classified blockwise. See, in the periodic table, the elements are classified into 4 blocks. See, one is S block, another is P block, D block and F block. There are 4 blocks in the periodic table. Group 1 and 2 elements, they are called as S block elements. Then elements of group 13 to 18, they are called as P block elements. Then the elements from group 3 to 12, they are called as D block elements. And now the lanthanides and actinides, which are placed separately in the periodic table, they are called as F block elements. Now, why group 1 and 2 elements are called as S block elements? See, these elements 1 and 2, they are called as S block elements because the last electron enter into the S orbital for group 1 and 2 elements. So, they are called as S block elements. Say, in the first group, the general outer electronic configuration for these elements is NS1, and for second group elements, the general electronic configuration is NS2. In general, the general electronic configuration, in the sense general valential electronic configuration, is NS1 to 2. So, general valential electronic configuration for group 1 and 2 elements or S block elements is NS1 to 2. The meaning of NS1 here means, see, hydrogen has 1s1 configuration, lithium has outer, sodium has 3s1 configuration, potassium has 4s1, ruby then 5s1, 6s1 and they have 7s1 configuration. All these elements, they have similar valential electronic configuration. That is what we call it as the periodicity. The property repeats after regular intervals because of this reason. They have similar valential electronic configuration. And group 1 elements, they are called as alkali metals, and group 2 elements are called as alkaline earth metals. Now, if you see the properties of the alkali metals, they are highly reactive elements. They never found in the native state in the nature. So, always they are available in the combined form. We never get pure elements in the earth's crust or in the nature. So, similarly, the first group elements, they always exhibit the oxidation state +1 in all its compounds. The second group elements, they exhibit the oxidation state of +2 in all its compounds. So, collectively these two are group 1 and group 2 metals are strong metallic in nature. So, metallic property increases on moving down the group. So, that is about the S block elements. Now, if you go for the P block elements, the elements placed in the group 13 to 18, they are P block elements. Now, the important point is the valence shell electronic configuration or the outer electronic configuration. The valence shell electronic configuration for this p block elements is NS2 NP 1 to 6. NS2 NP 1 to 6. So, group 13 elements have NS2 NP1 configuration, then 14 elements have, group 14 elements have NS2 NP2 configuration, then NP3, NP4, NP5 and NP6. Group 18 elements have NS2 NP6 configuration. Here the p orbitals are progressively filled here. Now, group 18 elements in the p block, they are called as noble gases. Group 17 elements are called as halogens. Group 16 elements are called as chalcogens, ore forming compound. Now, in the p block, we have gases on the top rightmost. See here, these are all gases: helium, then nitrogen, oxygen, fluorine, neon, chlorine, argon, krypton, xenon. These are all, okay. We have metals, non-metals and metalloids, all are present in the p block elements. But in case of alkali metals, except hydrogen, so all are metals. The position of the hydrogen is a problem. So, therefore, it is not studied along with the alkali metals. Hydrogen is studied separately. When we study the alkali metals, we keep hydrogen separate. Okay. Next, let us go for the D block elements. Now, group 3 to 12, they are coming under D block. So, these elements are also called as transition elements. These are also called as transition elements. Why they are called as transition elements? We have strong metals here. This side p block you have non-metals. When you move from left to right, then the metallic property gradually changes to non-metallic, and they form the D block elements are the bridging between highly reactive S and S block element, that is group 1 and 2, as well as the less reactive group 13 and 14 elements. So, thereby their property gradually changes. They form a bridge between group S block as well as between the P block, and the property changes gradually from metallic to non-metallic. That is the reason they are called as transition elements. They are called as transition elements, and all the D block elements, they are metals, no doubt. So, and these elements shows variable oxidation state. The transition elements, they are most of them are paramagnetic in nature. Many transition metals and transition metal compounds, they are used as catalysts. For example, iron or iron oxide is used as the catalyst in the manufacture of ammonia by Haber's process. Nickel, finely divided nickel, that is used as catalyst in hydrogenation of oils. So many examples are there. Vanadium pentoxide is also used as the catalyst. So, these are the metals which play very important role in the process called catalysis. Then the main point to be remembered, general valence shell electronic configuration for D block elements. The general electronic configuration, see, remember this, n minus 1 D 1 to 10 and then ns 0 to 2. Many students ask, what is this n? See, n minus 1 D, ns, your D block starts from 4th period, right? That means 4s is filled first. So, therefore, ns, if it is 4s, and N minus 1 is 3D. For scandium, your configuration is 3D1 and 4s2 outer electronic configuration. So, in a D block, we have 4 series of elements. One is 3D series, starts from scandium atomic number 21 to zinc. Then second transition series, 4D series, yttrium to cadmium. Then your 5D series, lanthanum 57, then hafnium 72 to mercury. 6D series starts from actinium, then the next element is rutherfordium. It continues like this. Okay. So, totally we have 1, 2, 3, 4 transition your D block, 4 series of D block elements. Okay. One is 3D, 4D, 5D and 6D elements. Okay. After that, the next block, that is F block elements. They are called as, F block elements are known as inner transition elements. Inner transition elements. See, in the F block we have lanthanoids. It starts from cerium 58 to lutetium. So, here lanthanum is head of the family. Lanthanum has to be this is lanthanum atomic number 57. All 14 lanthanoid elements from cerium 58 to lutetium, they have to be written in small block along with the lanthanum. So, but which is highly impossible. Total the information of 14 elements we cannot write here. So, that is the reason these 14 elements are placed separately, and since lanthanum is head of the family, we call them as lanthanoids. After that 5F series, lanthanum, this is 4F series. So, then 5F series, actinoids. See, the actinoids, again 14 elements from thorium 90 to lawrencium atomic number 103. So, these 14 elements, the 5F starts filling. So, these are called as 5F series. If the last electron enter in the s orbital, they are called as s block elements. If the last electron enter into the p orbital, they are called as p block elements. If the last electron enter into d orbital, they are called as d block elements. If the last electron enter into f orbital, we call them as f block elements. And coming to the f block elements, see, the general outer electronic configuration here for the f block elements, the general outer electronic configuration is n minus 2 f 1 to 14, then n minus 1 d 0 to 1, then ns 2. This is the valence shell electronic configuration, important one for the examination. N minus 2f 1 to 14, n minus 1 d 0 to 1 and ns 2. That means, so you are 4f, 5d and 6s. Okay. So, n is, if it is 6s, this is 5d, n minus 1d, then 4f. This is how we write the electronic configuration for general electronic configuration for the f block elements. So, now coming to the actinoids, all actinoids are radioactive elements. The elements which comes after uranium, they are called as transuranium elements. Now, in the periodic table, I told you metals are there, about 78% elements are metals. You know the metallic property, metals are good conductors of heat and electricity, they are malleable, they are ductile. You know, malleable, you can hammer them into plates, the metals can be drawn into wires, then they are good conductors of heat, good conductors of electricity. Metals are electropositive in character. The non-metals, you have non-metals. Non-metals are poor conductors of heat and electricity. Most of these non-metals are either gases or low melting solids. Then see, we have one more category elements called as metalloids. Metalloids, see the zigzag line which run down from silicon, germanium, silicon to germanium, arsenic, antimony, then tellurium. So this zigzag line which run down from silicon, see here zigzag line, that separates metals and non-metals. This side, whatever the elements comes this side, they are metals. The metals, the elements which comes like this, they are non-metals. Now let us see about the periodic trends in properties of elements. See, periodic trends, I told you, after a regular intervals of time, that means when you arrange the elements in the increasing order of their atomic number, after a regular interval of time, you get another element which has similar properties. That means the property of the elements repeats after regular elements. I told you, so lithium, sodium, potassium, these have similar properties. Beryllium, magnesium, calcium, strontium, barium, radium, they have similar chemical properties. Okay. Similarly, these elements are having similar chemical properties. That is because of the electronic configuration or valence shell electronic configuration. So this type of the repetition of the property, that's called as periodicity. Let us study the periodic trends in properties of elements. In that we will discuss about the physical properties. One is atomic radius. Atomic radius. What do you mean by atomic radius? So atomic radius is, what is an atom? You have a positively charged nucleus at the center, and then you have the shells around the nucleus in which electrons are there. Okay. So distance between the center of the nucleus and the outermost shell of electrons. Now it is not possible to find out the exact atomic radius. One thing is, a single atom cannot be isolated, then the radius of the atom is in the range of 1.2, approximately in the range of 1.2 into 10 to the power of minus 10 meters. This range, 10 to the power of minus 10 range, okay, or 1.2 angstroms we say. So this range is very small, you cannot imagine. Therefore, that is the one reason a single atom cannot be isolated, atom is very, very small. The other reason is, we said that electron has a wave character. Electron has a wave character, we call it as electron density or electron cloud. Electron density or electron cloud. That means due to the wave character, now due to the wave character, say the electrons move like this, the electron, it has a wave character. There is no proper clear boundary for the electron cloud. Understood? There is no clear boundary for the electron cloud. That is the reason we cannot find out the atomic radius. Then what? We can find out the radius of the atom in the bonded state. If there is a covalent bond, you can find out covalent radius. If there is ionic bond, we can find out ionic radius. If there is van der Waals force of attraction between the molecules, then or the between the atoms in case of inert gases, we can find out the van der Waals radius, or we can find out the metallic radius in case of metals. We will see this covalent radius. Covalent radius. What is covalent radius? To explain the covalent radius, to understand the covalent radius, we have to go for the covalent bond. You know that. What is covalent bond? Covalent bond is formed by the sharing of an electron, one or more electron pairs between the two atoms. Okay. Consider this is an atom, this is the nucleus of an atom. Take two identical atoms, this is atom A, and then this is atom, another atom, this is also A. This is the nucleus of this atom. Okay, this is the nucleus of another atom. These two, the orbitals overlap. In this overlapped region, the electron gets paired up, thereby a covalent bond is formed between these two atoms, and the internuclear distance, what we call, okay, the distance between the two nuclei, that is called as internuclear distance, or we call it as a bond length. Bond length. Now, covalent radius means half of the internuclear distance. This is the distance between these two nuclei. Half of this distance, that is called as a covalent radius. Half the distance between the nuclei of two atoms which are bonded covalently by a single bond. There should be a single bond between these two, that is one condition. Both the atoms should be identical atoms. So, then we can talk about the covalent radius. Bonding should be the bond between these two, a covalent bond. Okay. Now, if you take the chlorine atom, Cl2 molecule, the internuclear distance is 198 picometer. In case of chlorine molecule, internuclear distance, what you call bond length. Therefore, the atomic radius is equal to 198 divided by 2, that is equal to 99 picometer. That is equal to 99 picometer. So, 99 picometer is the covalent radius of chlorine atom, right. So, in case of metals, the property of the metals could not be explained on the basis of your covalent bond or ionic bond or coordinate bond. Any other bonds could not explain the property of the metals. Metals have some special properties, high electrical conductivity, I said, malleability, ductility, all these properties cannot be explained from any of these bonds. Later, another bond called metallic bond is introduced. We are going to study that metallic bond in first PUC only. So, let me explain a little bit about the metallic bond. See, in case of metals, you have positively charged ions, we call them as kernels also, or cores are there. See, these are the positively charged kernels, okay, and then they are arranged in a regular 3-dimensional, okay, this is a 3-dimensional arrangement is there. Now, these are metal cores, and the valence electrons, they move throughout the crystal. We call the metals as metallic crystals. The valence electrons move throughout the crystal within the boundaries. Okay. So, these electrons are there, so they move within the boundaries. Then the distance, half of the distance between the two adjacent metallic cores, that is called as metallic radius. In case of metals, we can talk about metallic radius, that is half of the internuclear distance separating the metal cores in the metallic crystal, that is called as metallic radius. Okay. Now, let us see the variation of atomic radius in the periodic table, its trends in the periodic table. Across a period, what happens? Down the group, what happens? You can watch the values of the atomic radius. The radius is given in picometer. You have the elements like here: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, right? Just to observe the trends. Now, atomic radius depends on what? On what factor it depends? One thing is, the atomic radius depends on the effective nuclear charge. We call it as effective nuclear charge, or the nuclear charge is the one factor. If you have only one shell, you consider this is the nucleus and this is the shell, this is another, you take another atom with, see, positive charge in the nucleus is because of the protons present here. You take lithium here and you take fluorine. So, lithium, you have in the valence shell, you have only one electron, fine. Okay. Consider there is an electron here, here also you have an electron. Fluorine, you have 7 electrons, of course. In the nucleus, you have 3 positive charges. In case for lithium, atomic number 3, 9. You have 9 positive charges in the nucleus. You have only less positive charge. Here you have so many positive charges. Then what happens? There is a force of attraction between, electrostatic force of attraction between the nucleus and the outer electrons. So, these electrons are held by electrostatic force of attraction. The electrons are held, tightly held. Okay. So, if you consider the force of attraction, if the nuclear charge is more, there will be greater force of attraction on the electron, because the n value remains same for this and this. Therefore, as the effective nuclear charge increases or the nuclear charge increases, the force of attraction on this electron increases. This electron is more tightly held, this electron is held little loosely. Then you can think about the radius. If the electron is held tightly, it will be pulled inside. Okay. Electron cloud is pulled inside. Therefore, naturally its size should be smaller. Okay. Same trend you can observe. The second factor, when I said the radius of the atom or the size of the atom depends on, first factor, effective nuclear charge. Second factor is number of shells. Okay. Number of shells around the nucleus. This atom may have, lithium has 2 shells, one is K shell, L shell. If you go for sodium, so this sodium has how many shells? So, this is K shell, this is L shell, this is the nucleus, then one more shell is there. As the number of shells increases, naturally you only tell now, this has as the number of shells increases, what happens? As the number of shells increases, the atomic radius increases. Atomic radius increases. That is the second factor. Third factor is a screening effect. That is called as screening effect or shielding effect. Okay. So, you have studied the screening effect or shielding effect in second unit of chemistry, that is in the atomic structure. Okay. I hope you know that screening effect. It plays an important role in the atomic radius. So, let us see the trends in the periodic table. So, lithium atomic number 3, beryllium 4, 5, 6, 7, 8, 9. Okay. Now, if you move like this, from lithium to fluorine, effective nuclear charge increases. I told you, as the effective, see, electrons are added into the same principal shell. So, lithium, the electronic configuration is, see, 1s2 and 2s1. You have two shells, K shell and L shell. We are filling the L shell here. After filling, see, L shell is filled here, S1, this has 2s2, then 2p1, 2p2, 2p3, 2p4, 2p5. So, electrons are added into the same shell, and the inner core is what? 1s. The inner core of electrons remains same for these elements. That means shielding effect doesn't changes, only the effective nuclear charge increases. Thereby, the electrons are held tightly by the nucleus. You can see the values. So, that is, the atomic radius decreases. Atomic radius decreases from lithium to fluorine. That is because of increase in the effective nuclear charge. If you go down, just see these values. You have sodium, potassium, rubidium, cesium and francium. Then this side you have fluorine, chlorine, bromine, iodine, astatine, right? On moving down the group, you have seen the configuration. See, here you fill the n value, here it is equal to 2 period number, you have only 2 shells, here we are adding one more shell, 3 shells are there, 4 shells, 5 shells, 6 shells and 7 shells are there for this francium. Okay. As you move down the group, new shells are added. Thereby, the atomic radius increases from on moving down the group. It is true for all the groups. It is true for all the groups. What is to be remembered? Atomic radius decreases across a period from left to right. Then down the group, atomic radius increases. This is because of increase in the effective nuclear charge. So, down the group, increase in the atomic radius, that is because of addition of new shells. Let us go for the next concept, that is ionic radius. Ionic radius. What is ionic radius? Ionic radius is the distance between the nucleus of an ion and the point up to which the nuclear charge has the influence on its electron cloud. Okay. Listen, ionic radius is the distance between the nucleus of an ion, a positively charged nucleus, and point up to which the nuclear charge has the influence on its electron cloud. That is ionic radius. In case of ionic compounds, we can calculate the ionic radius. In case of ionic radius, the very important point to be remembered for the examination point also, radius of the cation and its neutral atom. For example, Na. Na, it is converted to Na plus. How you get Na plus? The electronic configuration of sodium, atomic number 11, we can say 281, 1s2, 2s2, 2p6 and then 3s1. Now, in Na plus, in its compounds normally, in the ionic bond also, covalent bond also, the atoms tries to have the 8 electrons in the valence shell, that is called as octet. How to get the octet? Either by losing the electron, gaining the electron, or by sharing the electron. That is actually basis for the chemical bonding. All the elements tries to have the stable inert gas configuration. They are monoatomic. Okay. So, tries to have the 8 electrons in the valence shell. That is called as octet. So, if octet is there, or in other words, they tries to have the nearest inert gas configuration. Sodium atomic number 11, its nearest inert gas configuration for sodium, say, is neon atomic number 10. Anyway, we are discussing about ionic radius. Na is converted to Na plus. How it is converted to Na plus? It loses an electron, loses one electron, and thereby it removes an electron is removed here. So, the configuration becomes 2 and 8. Now, in both the cases, number of protons in the nucleus remains same. Here you have 11 protons, in Na plus also 11 protons. In this case, this 11 protons attract the 11 electrons. In this case, 1 electron is less. So, 11 protons attracts the 10 electrons. Naturally, the force of attraction on the electrons will be more here, or 11 protons can attract the 10 electrons more tightly. Thereby, the electron cloud shrinks. So, radius of Na plus is smaller than the radius of Na. For any atom, radius of the cation is smaller than its neutral atom. So, it is electrically neutral one, right. So, if you see that radius of Na is 186 picometer and radius of Na plus is 95 picometer. See the difference. But in case of Na and Na plus, so outermost shell itself vanishes. Okay. Here there are 3 shells, K shell, L shell, M shell is there, but you have only 2 shells are there, K and L shells are there. So, that is another reason why it has so less ionic radius. Similarly, radius of the anion and its neutral atom. Cation is formed by losing one or more electrons. Then anion is formed by gaining one or more electrons. For example, Cl plus electron, it becomes Cl minus. Cl plus electron gives Cl minus. F plus electron gives F minus. Okay. Now, radius of the fluorine is 64 picometer. After gaining electron, it is 136 picometer, F minus. See how the negative ion is formed? Negative ion is formed by gaining one or more electrons. Now, fluorine atomic number 9. Okay, it has 9 protons in the nucleus and 9 electrons in its shells. Totally 9 protons attract 9 electrons. In this case, an electron is added, thereby number of electrons is 10. Number of protons in the nucleus remains same. Now, you only tell me what can be the ionic radius. So, as the number of electrons increases, then its radius increases, or the electrons go away from the nucleus. So, that is the reason the radius of F minus is greater than the radius of its neutral atom, or radius of cation is smaller than its neutral atom, radius of anion is larger than its neutral atom. Okay. Let us discuss one more important concept, isoelectronic species. isoelectronic species. Isoelectronic species, that means iso, same, electronic, same number of electronics. The species may be atoms or ions containing same number of electrons, they are called as isoelectronic species. For example, N minus 3, O minus 2, F minus, Na plus, Mg 2 plus, Al 3 plus, all these are having same number of electrons. N minus 3, atomic number is 7, minus 3 charge because it has gained 3 electrons. So, number of protons and number of electrons. Number of protons here you have 7, electrons 10. O minus 2, the atomic number of oxygen is 8, 8 protons in the nucleus, 10 electrons. F minus 7, 9 protons in the nucleus, 10 electrons. Sodium 11 protons, 10 electrons. Again protons are 12, again 10 electrons for the magnesium 2 plus. These are the number of electrons. Electrons are having negative charge, protons are having positive charge. I told you there is the force of attraction. Look here the number of protons and compare the number of protons and electrons. So, 7 protons has to attract, catch hold of 10 electrons. Here 12 protons has to catch hold of this 10 electrons. Naturally, force of attraction will be greater here. Okay. So, the electron cloud comes nearer to the nucleus, thereby Mg2 plus has smaller size compared to size of N minus 3. Okay. Therefore, the atomic radius decreases in the order like this. For examination, they may ask you to arrange them in the increasing order of the atomic radius, what are isoelectronic species, or out of among any two, N minus 3 and Na plus, which one has smaller size, which one has greater size. Like this, the questions may be asked. Okay. Let us move to another very important concept, ionization enthalpy. Ionization enthalpy, delta H I. I stands for ionization. Delta H, change in enthalpy. It may be the new term for you. So, you are going to study this term enthalpy in thermodynamics in detail. Enthalpy means heat content. Ionization enthalpy, delta H, change in enthalpy. See, in any chemical reaction or process, heat change takes place. Two type of the enthalpy change takes place. That is, delta H can be positive or delta H can be negative. Okay. If delta H positive means heat is absorbed by the system. Okay. So, delta H is a thermodynamic sign convention. Delta H positive, we call that reaction as endothermic. Delta H negative means exothermic, heat is released. One is endothermic, positive, delta H if you say negative, then it is called as exothermic. Let us see what about the ionization enthalpy or delta H factor for ionization. See, ionization means a removal of the electron. You take X atom, X gaseous, it gives, you remove an electron, X plus gaseous plus E minus. Now, what is ionization enthalpy? Ionization enthalpy means the energy required to remove an electron from an isolated gaseous neutral atom. Listen carefully. Ionization enthalpy, it is the energy required. We cannot say enthalpy change. Energy required. Why energy required? To remove an electron from an atom. Always you have to supply the energy. Simply you cannot take out the electron from any species, any atom or any ion. To remove an electron, you have to supply energy to the atom. Then only the electron comes out. Okay? Now, according to definition what I said, energy required to remove an electron from an isolated gaseous neutral atom. Atom should be in the isolated state. Isolated gaseous atom you can't get in the solid state or in the liquid state. You can get the isolated atom in the gaseous state. In case of sodium, what happens? Sodium, sodium metal is solid. To calculate the ionization enthalpy, Na first to convert into Na gaseous. Okay, whatever the energy required here to convert Na to Na gaseous, that is called as sublimation enthalpy. You have to sublime that. Solid substance has to be converted to gaseous substance. Now, Na gaseous. After that, you get Na plus gaseous plus electron. Now, energy whatever required to remove an electron from Na gaseous to Na gaseous, to remove an electron from this gaseous sodium atom, that is called as ionization enthalpy. Look here, the energy required to remove the first electron from an atom, that is called as first ionization enthalpy. Okay, let me call it as IE1. If you want to remove another electron from this species, X plus gaseous, it gives X 2 plus gaseous, one more positive charge increases because you have removed another electron, plus E. Let me call it as IE2. You can still remove the electron. Okay. Normally, the second ionization enthalpy is always greater than first ionization enthalpy. So, IE2 is greater than IE1. Second ionization enthalpy is greater than the first ionization enthalpy. Look here, the number of electrons decreases and the nuclear charge remains same. Thereby, the force of attraction on the electrons increases. So, ionization enthalpy increases. Energy required to remove an electron increases. Now, ionization enthalpy, I told you, it is always a positive quantity. Now, what is the unit for the ionization enthalpy? Ionization enthalpy is expressed in kilojoules per mole. According to definition, energy required to remove an electron from an isolated gaseous neutral atom, right? But the unit is per mole calculation is given. Mole means Avogadro number of particles, 6.022 into 10 raised to 23. Now, you take 6.022 into 10 raised to 23 atoms, convert them into gaseous state, then remove each one electron from all these Avogadro number of atoms, then whatever the energy required to remove the electron for 1 mole of the atoms, that is the unit. So unit is kilojoules per mole. Calculation is for per mole. Now, see, ionization enthalpy. What are the factors on which your ionization enthalpy depends? First one is atomic radius or size of the atom. Okay. Atomic radius again depends on your effective nuclear charge, I said. The ionization enthalpy depends on effective nuclear charge. Second factor, atomic radius. You take two atoms, a smaller atom and a bigger atom. There is an electron here, there is an electron here. Naturally, the force of attraction on this atom, so on this electron, is more in case of smaller atom. The force of attraction of the nucleus on this electron, which is away from the nucleus, definitely it will be less. So less energy is required to remove this electron and more energy is required to remove this electron. That is regarding the atomic radius. Again, effective nuclear charge. If the effective nuclear charge is greater, the force of attraction on the nucleus is greater, therefore high energy is required to remove an electron. And third factor is electronic configuration. Electronic configuration. Especially in case of electronic configuration, the stable electronic configuration. If the orbitals are filled completely, it attains stability. If the orbitals are half filled, then also it attains stability. Okay. What do you mean by half filled? In case of p orbitals, you have 3, in case of p subshells, you have 3 orbitals. In a d subshell, there are 5d orbitals, right? If these are singly occupied, p3 configuration, half filled, d5 configuration, that is half filled. F, if you talk about the F14 is half filled, it attains stability. It's very difficult to remove the electron from the stable atom or need more energy to remove the electron. So if it is completely filled, means p6 configuration, d10 configuration is completely filled for d orbitals, F14 is there, that is completely filled situation. Now let us study, by keeping these factors in mind, we will study the ionization enthalpy. Trends of ionization enthalpy across the period, down the group. In general, see, you have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. After that you have neon. Okay. Down the group, sodium, potassium, rubidium, cesium, right? In general, ionization enthalpy increases across a period. To remember, what is the general trend? In general, ionization enthalpy increases across a period, right? Then, what is the trend down the group? Down the group, ionization enthalpy decreases. Why it increases? That is because of increase in, say, from left to right across the period, nuclear charge increases, atomic radius decreases, thereby the electrons are held tightly by the nucleus, removal of the electron is difficult, more energy has to be supplied. That is the reason in general it increases. In general, down the group ionization enthalpy decreases, because down the group new shells are added, atomic radius goes on increases, the electrons are away from the nucleus, force of attraction on the nucleus decreases, thereby removal of the electron is little easier. So, the ionization enthalpy decreases down the group. ಈಗ these group 18 elements, they have very high ionization enthalpy. What's the reason? Because they have stable, completely filled configuration. They have attained extra stability. Once they attain the stability, they, by losing an electron, they become unstable. So, they don't try to lose the electron very easily. Hence, very high energy is needed to remove the electron from this atom. Alkali metals, they have very low ionization enthalpy, because by losing an electron they attain stability. They always tries to lose the electron. So, ionization enthalpy is least for the alkali metals and very high for the group 18 elements, that is for inert gases. Now, this is the general trend, but important point here is just note down the values. You can see these values: ionization enthalpy of beryllium and boron. Ionization enthalpy of boron is less than beryllium. This is abnormality. Why? See, beryllium you have 2s2 configuration. The s orbital is completely filled. That's one reason. And boron configuration is 2s2 2p1, and inner core helium core is there for both. 1s2 2s2. Here it is 1s2 2s2 2p1. Here we are removing the s electron. Here you have to remove the p electron. Now, s electron, you know, the s orbital is very nearer to the nucleus because of this spherical shape. P orbitals are away from the nucleus. Because of its shape, it has a dumbbell shape, and the electron density is very nearer here in case of beryllium. So, the electrons are held tightly here. One is shape is one factor, shape of the orbital. Second one is the orbital is filled. So, it has little higher ionization enthalpy than that of boron, because we are removing the p electron from here. Higher means it's not very high. Actually, if you arrange the increasing order, it goes here. After boron comes first, ionization enthalpy, then goes to beryllium. One step ahead, only one step ahead. Similarly, the ionization enthalpy of nitrogen and oxygen, just see the values. The value of ionization enthalpy of nitrogen is higher than that of oxygen. Why it is so? Nitrogen has half filled configuration. So, p orbitals, this has 2s2 2p3 configuration, p3 state. See here. So, in case of nitrogen, p orbitals are half filled. You know, half filled electronic configuration attains stability, gives the stability. So, high energy is needed to remove the electron from the stable configuration. That you go for oxygen. So, 1, 2, 3 and 4th electron is there. So, here the 4th p electron is paired, okay, and due to electron repulsion here, electron repulsion, removal of this 4th electron from the p is very little bit easier. That's the reason the ionization enthalpy of nitrogen is more than that of oxygen. These abnormalities you have to remember. Okay. Then we discussed about the in general trends. Here no doubt the ionization enthalpy decreases down the group. Okay. Thank you.